Hi everyone. So welcome again to the Shannon channel. Today we have Ravi Tandon from the University of Arizona, and he's going to talk about communication efficient distributed learning. So we're all really excited to hear his talk.
Okay, thank you, Salim. So should I screen share now?
Yeah.
Okay. All right. So okay, can you see the slides?
Yeah. Yeah. We can see this.
Okay. So I don't know which title I gave you. It's sort of a slightly different title, but pretty much content will be the same. So today I'll talk about information theoretic trade-offs in large-scale distributed learning. And this is a joint work with my PhD student, Mohammad Atia. So let me get started. Uh, I think we have to pay a homage to big data, which is giving us some interesting problems to solve every day. What this infographic shows is a bunch of different applications and the scale and speed at which how much data is being collected and how much money is being made, especially if you see some of these numbers, particularly if you look at Amazon, how much money it's making in sales every minute of the day. And this is 2017, so I'm guessing the scale is getting bigger day by day. And the amount of data that we are processing, the growth in the amount of data that we are going to process is also increasing at a very rapid pace. So the question is then, how do we handle large scale data sets? And what is the right way to process large scale data sets in an efficient manner? So to this end, there has been a lot of recent interest in large-scale distributed computing for big data applications by a variety of big players in this area. So to give you some sample, Azure, Microsoft has its own Azure service, Google, Amazon, Apache Spark. So these are some of the frameworks and tools which are quite popular for large-scale distributed data processing and computation. Without going into the similarities and differences of each one of them, what I want to highlight next is what is the common underlying theme and what are the common underlying sort of fundamental building blocks in such large scale distributed computing frameworks. Everybody is able to hear me, Salim?
Yeah. We can hear you.
Okay.
We just muted ourselves so we can we don't have problem.
Okay, good. So until unless there's an issue, just let me know. I'll keep
Yeah.
going.
Sure.
Okay, cool. So distributed computing can be sort of divided into four phases, and I'd like to call it as the four phase comprising of communication, storage, computation, fusion, and sort of each epoch or each iteration is sort of broken down into these three or four phases. So, for instance, the typical setting is that you have a master node which is trying to do some large scale computation. And the goal is to do these computation through a distributed cluster of nodes. And typically, there is some communication involved as the master node sends some data or splits the data into smaller chunks and sends this data to a cluster of workers. Each worker has some local storage available to it. So there is data storage involved. And then some computation tasks are assigned. So some processing happens at these workers. And then these workers feed back what they have done to the master node for either accumulation or aggregation. And therefore, there is this back and forth between the master and the cluster of workers. Okay. So the ultimate goal is to sort of understand the trade-offs or optimal trade-offs between the key resources that are available and what are the key objectives that we want to accomplish. So in this sort of graphic, I've shown some of the things that at least I'm interested in, and at least a lot of people currently in information and coding theory community are looking at. So if we go over some of these items, so first is the computation aspect. How much computation is each worker doing? The second is the communication aspect. How much overhead of communication is involved essentially in this back and forth between master and worker nodes. The third is the amount of storage. How much storage availability do I have at each worker? How many number of workers do I have in the system? Do I have 5 workers in the system or 50 workers or 500 workers in the system? Then another aspect is latency. And latency is sort of inherently a function of all of these items. And finally, accuracy. So if you ask different people in different communities, people have different objectives. If you ask somebody in the machine learning data mining community, they are perhaps more interested in the accuracy of the model that you learn. Whereas if you ask people in the information theory community, at least as of now, majority of them are potentially interested in the interesting trade-offs between communication, computation, storage, and latency. So what has happened in the last few years, there has been an exponential rise in the sort of intersection between leveraging information and coding theoretic tools and applying them to problems related in distributed computing. So what I'm going to do next is sort of give you a high-level overview of at least a couple of problems that I'm aware of that people are working on, and I think some of you are already aware of them. But I think it might be a good way to know, what are interesting problems in the area. And then I'm going to focus the rest of my talk on one particular problem, which is on data shuffling, distributed data shuffling. Okay. So before we move on, I want to start by saying that the end-to-end time. So say if you want to do a large-scale computational task, the end-to-end time for computation can be sort of divided into two parts. The first is the time for doing the actual computation, and the second is the time for communication between master and worker nodes. So recently, there has been a lot of interest in understanding the bottleneck that arises due to distributed computation, which has been studied under the name of this so-called Straggler Problem. So what is the Straggler Problem? Basically, the problem is that if you assign a task to multiple workers, then some workers might be slower than usual. So, or in other words, different workers may work at different speeds. And if a task has to be finished when all of these workers finish their individual tasks, then you are essentially limited by the slowest one. So then the goal becomes, how do I handle this problem of slow workers in the system? And so computation time is naturally limited due to the slowest worker. So before coding theory was sort of first used to attack this problem, there were different other approaches in the literature, and some of them originating in the operating systems community. So for instance, one approach which is actually quite old is something called work stealing, in which if a faster worker has finished his job, then he can take over the work of slower workers. So this approach is work stealing. And then the other recent approach is what I just mentioned, which is something called coded computation. So coded computation is a way to introduce redundancy in distributed computation in a structured way, so that when if I give a task to a set of workers, then if any subset of them respond, then one should be able to recover the original task that was assigned. Okay. Of course, there are other approaches as well, something known as work exchange, which is one of my works, but I'm not going to go into details of that approach at this point. So to give you an example of this coded computation, how coding can help in mitigating the impact of stragglers, suppose we are interested in doing matrix multiplication. So say we want to do A times X, and let's say we break the matrix A into two parts, A1 and A2. So essentially our goal is to do A1X and A2X in a distributed manner. And say we have two workers, so we assign these two tasks to the two workers. So clearly, this assignment doesn't have any failure tolerance. So even if one worker fails, or if second worker is very slow in responding, then will not be able to finish the task appropriately. So what can we do? We can introduce redundancy in the system. So for instance, we can use repetition codes, which is the simplest form of repetition. So let's say we create two more copies of these tasks. So essentially, I have four workers in the system now, and workers 1 and 3 do the same task, and workers 2 and 4 do the same task. So this is fine. Hopefully, this should be better than having only two workers. But the issue in this repetition-based approach is that I still only have failure tolerance of one worker. So it can tolerate one failure. It can tolerate one very slow node. So of course, this is not good, because Shannon tells us how to introduce redundancy. And I think coding theory is a natural way to introduce redundancy in a very efficient way. So instead, we can use MDS codes, for instance. We can assign linear combinations. We can first create linear combinations or parities of the A matrix and assign A1x, A2x, A1 plus A2x, and A1 minus A2x as the four tasks to the four workers. So essentially, you can view these breaking and splitting of A's into different chunks as being done through a 4-to MDS code, which means that any 2 out of 4 workers are sufficient to recover the original matrix multiplication task of AX. Okay. So there has been a lot of interest in understanding the role of coding for particularly matrix multiplication problems. So for instance, if one can use NK MDS codes, where N is the number of workers and K is the number of divisions, and there's a natural trade-off. So for instance, N3 MDS code would give you a trade-off as a function of time versus N, the number of workers, and N4 MDS codes will give you a slightly different trade-off. So essentially, you would wait for 4 workers to respond as opposed to 3 workers to respond. So essentially, the time goes up for the same number of workers. Okay. Of course, the trade-off is what? Trade-off is that every worker does a little bit less amount of computation. If you think about N3 MDS code versus N4 MDS code, then each worker is doing 1/3 of the job versus 1/4 of the job.
Okay. Ravi, what is the model you have here on the weighting? Is it exponential?
This is very general, Salim. I mean, essentially, okay. Let's see. Yeah, I mean, I'm not going into details of how exactly you do this.
Okay.
I just want to highlight, at least 2 examples different from what I'm going to talk about, where coding is being used at this point, or people are exploring the role of coding. Okay. So there has been recent work in this coded distributed computing. For instance, coded matrix multiplication using one-dimensional MDS codes. This was looked at by Lee and the group of Ramchandran in 2015. Then product codes were introduced in 2017. And then polynomial codes, the work of a group of Salman Agasti-Meher at USC. And then gradient coding was another interesting set of papers came out on gradient coding, where the goal was to use codes to speed up distributed gradient descent. So there the goal is to essentially compute the sum of gradients where where gradients of different data points are assigned to different workers. Okay. And then coded convolution. So doing convolutions of such as FFT and related operations and using codes to speed up these operations in a distributed manner. This was looked at by a group from, I think, Pulkit in 2016. So a bunch of different works on exploiting codes for these type of problems, particularly for linear operations. Okay. In addition to this line of work, the other, now coming back to the end-to-end bottleneck. So the other bottleneck is the communication-related bottleneck. So communication-related bottleneck happens in many ways. So let me explain a few pointers. So for instance, of course, there is an initial data delivery that master node sends some data to the workers. And typically, this is sort of one-time cost. And the processing essentially happens at the local storage at the nodes. But the communication bottleneck happens when the data assignments change over time. So this data assignment changing over time could happen in many scenarios. So one scenario which I will focus on is something called data shuffling or reassignment of work. And there, in such scenarios, intermediate communication is needed in such problems. And the recent trend has been to understand the role of coding, how to use coding to reduce the communication overhead. Okay. So one example which I want to highlight is something which Salman's group introduced, which is coded MapReduce. So if some of you are aware of this MapReduce architecture, typically what is done is that you have some functions which one wants to compute as a function of the keys, and or think of these as, there are 6 files or 6 functions you want to compute. Each function is inherently a function of 3 color-coded files. So what we do is we do distributed assignments or mappings to these workers. Hold on, let me move this hide business from here. Okay. And once these initial mappings, so for instance, if you look at this figure, worker 1 is assigned red chunks 1 and 2, yellow chunks 1 and 2, and green chunks 1 and 2, and so on and so forth. So once these workers do the local computations, then the reducing operation involves collection of all the red chunks at worker 1, all the yellow chunks at worker 2, and so on and so forth. So in order to do this reducing, we need to send 12 intermediate calculations in total. So it turns out that this overhead of 12 can be significantly reduced by using coded transmission. So how can we do coded transmission? The idea is to do a little bit more computation. So we can do more computation in the following way, that each worker, instead of doing only 2 computations per color, does 4 computations per color. So if you look at this new figure, worker 1 is doing 4 computations on the red file, 4 on the yellow file, and 4 on the green file. So now the extra computation can act as side information. And if once you have side information, then you can send these coded intermediate processed results. So one can send yellow 1 XORed with the green 3, which will be useful for 2 guys simultaneously. And similarly, the other 2 coded chunks will also be useful for 2 guys simultaneously. So, so this sort of is the main idea behind coded MapReduce. And the clever trick is to, assign the additional computation or the redundant computation, and then leverage the redundant computation by doing this coded transmission to reduce the communication overhead. So the idea again is to summarize that one can do more computation per worker, which can potentially lead to lower communication. So there's an inherent trade-off between communication and computation. Okay. So what is this talk about? Any questions so far?
I have one. In this, in the graph, the computation is going to 0. Is that like you're just doing all the computation in 1? What is this?
Yeah, so computation, if everybody does all the computation, so
then they don't need to transmit anything. So this is just like the trade-off.
Exactly. Yeah, I mean, I'm not showing the exact trade-off here. I'm just trying to, show the trend of the trade-off, that you can computation to reduce the communication. That's all I'm showing.
Okay. But the idea that it goes to 0, okay.
Yeah, so communication goes to 0 by increasing the amount of computation. That's
so in this model, there is no master, so every node has to have all the results in the end?
Yes. So no. So worker 1 needs to know all the red chunks, all the 6 red processed chunks.
Okay.
Worker 2 is assigned to process all the yellow chunks, and worker 3 is assigned to process all the green chunks.
But you give them extra chunks, like redundant chunks, to be able.
Yes, so you give them extra chunks to process.
Okay.
So you sort of assume that everybody has all the data, but now how much computation is each guy going to do?
So here the reducers are also the mappers themselves? Or?
Yes, so yeah, exactly. So you can think of these as each node is sort of doing some local computation, and then from that local computation, along with the communication, each worker should be able to get a certain type of processed results. That's the goal.
Worker 1 should get the red, 2 the yellow, and 3 the green. That's the goal.
Yes. So worker 1 should get all the red 6 chunks. Worker 2 should get all the yellow chunks, and so on and so forth.
And what you're saying is that we can do faster if we kind of mix these.
No. So what we can do is if you go to the, so let me go back. Yeah. So think about this scenario. So everybody is assigned only 2 computations per color.
So why can't I just, if the goal is to give worker 1 the red, right? Why can't I just give all the 6 to worker 1 and all the yellow?
So maybe the reason for that is, as far as I understand, and again, that's a very good question in my opinion. I think if you give the same colors to each guy, maybe that might, the computations might not be balanced. So maybe the red computations might require more time than the green computations.
Okay, so you want some node balancing?
So what I mean by balanced is, do you understand what I'm saying?
Load balancing.
I'm sorry?
Like it's kind of like to achieve some load balancing among the.
Yeah, that's what my understanding is. I think the natural, yes, I think that's a very good question, and that comes to my mind as well when I read papers on this coded MapReduce, that if everybody is to get locally, for instance, for this example, only six colors, then why shouldn't I assign all 6 of the same color to each of the 3 workers? So I think.
But then, isn't the model here that each guy does 2 tasks? That like it's the blue thing over them, right?
Right.
If you want everyone to have, like, if you want the red guy to have all the red guys, he would have to have 6 tasks.
He would need to get all the 6 items in red.
So this is what I'm saying. I think the problem here is precisely that: is fix a number of tasks.
Okay.
So here you're giving 2 tasks to each person, And that's what you're not able to do. You can't do 6 things with 2 tasks for each person, like in one place. They have to be in different places. Isn't it that, or am I understanding?
I don't understand your point. Can you say that again?
The way that I'm seeing, so 1 and 2 are tasks 1 and 2, right?
Right.
And then you have tasks 3 and 4.
No, 1 and okay. So
What is this?
Let's look at the top 6 files. So think of this as 1, 2, 3, 4, 5, 6 in blue. So think of these as 6 files. Okay. And I want to compute a function of all these 6 files. And there are 3 functions I want to compute. Okay. I want to compute 3 functions of these 6 files. So worker 1 has files 1 and 2. Worker 2 has files 3 and 4. Worker 3 has files 5 and 6. So each worker is doing local computations on the 2 files that it is assigned.
Yes.
Okay.
What does the color mean here? Different functions?
Colors are different functions.
Oh, okay.
Colors are different functions. So what you see at the top are the 6 files. So worker 1 is assigned tasks on files 1 and 2. So it computes the 3 tasks, red, yellow, and green, on files 1 and 2.
Okay.
Okay.
Yeah, I have one question. So initially, you need to transmit 4 files to each worker if you use coded computing, right?
Yes, initially we need to send 4, exactly.
So that's
yes.
more communication.
Yes.
Right.
Yeah, so 4 per worker, so therefore total would be 12.
But
so
how do you measure the communication saving, like the total communication?
So if you look at this figure currently, what I'm showing in the figure right now, then you would send 4 to each worker. Worker 1 would need 3, 4, 5, 6 in red, right? So 4 per worker would give you 12 in total. Now the idea is that if I assign more computation per worker, so now let's say worker 1 is doing 1, 2, 3, 4.
Yeah, I mean they have all the files. You don't need to transmit files to them.
You don't need to transmit files to them. Yes. That's a good question for coded MapReduce authors, but again, I think
files are larger than the function value, right?
Right. My understanding is that maybe the operations on these files are potentially sequential, or you want to do some sort of load balancing so that not every worker is operating on one single function on all the 6 files. That's my understanding. That's why you want to sort of balance it out across the workers to maintain the even nature of the load of computation across the workers. That's my understanding. Okay.
I see.
Yeah. Okay, so by doing this additional computation, we can reduce the communication to 3 symbols as opposed to 12. So of course, there's a trade-off now between communication and computation. Okay, so again, there is a bunch of works on MapReduce setting and generalizations. So let me now go and talk about the model that we worked on over the last year and a half. So before introducing the actual problem, so let me tell you the motivation behind looking at this problem. So this is sort of a basic setup. Let's say we are interested in training a model for over a large scale data set. So let's say we have n data points, and each data point has a label. And let's assume that all the inputs are of dimension d. So the goal is to come up with some prediction model y hat, which is some function of the input x. And the way people do it is, through this empirical risk minimization framework, where they define sort of an element-wise loss function between the input x and the output y, which is of course a function of the prediction model f that you pick. And then the goal is to devise or learn the parameters of the prediction model, which gives us the smallest empirical risk. So the goal is to minimize or pick that model f, or pick parameters of f, which gives me the smallest empirical risk. So for instance, you could pick absolute loss or square loss and log loss, or that's not necessarily fixed, so it depends on the application at hand. So more often than not, this optimization problem is tricky to solve in a closed form. So analytical solutions are almost very rare, particularly when the number of data points is huge and the model might be complex. So people, of course, resort to numerical approaches such as gradient descent. So for instance, we can update the parameters of model f. F at time t plus 1 is the model parameters f at time t minus some learning rate alpha times the sum of the gradients of the loss function evaluated over all points I going from 1 to n. Okay, so I guess everybody knows gradient descent. But the issue in this gradient descent is this batch gradient descent is that all of these n gradients need to be computed for every iteration which is indexed by time t. So there are two ways people try to speed up gradient descent. So one speed up we can do by introducing stochasticity into the problem, which is very popular, which is the stochastic gradient descent and its variations. And the idea is that instead of computing all the n gradients at each time, we can pick an item at random, any one of these I going from 1 to any data point at random, compute the gradient, and then take the step from time t to time t plus 1. The basic idea behind SGD, or stochastic gradient descent, is that in expectation, I'm doing the right thing. So it all depends on how much is the variance, or in other words, how bad is the expected gradient to the two gradient, and what is the difference between these two. So as I said, batch gradient requires calculations of all the n gradients, and there are a variety of stochastic variations. I have just listed a few here: stochastic gradient descent, incremental gradient, random reshuffling, and there are a bunch of others such as variance reducing SGD, and so on and so forth. So one trick that people use quite a lot is something called random reshuffling of data points when they try to implement gradient descent or stochastic gradient descent in distributed settings. So let me explain what I mean by that. So gradient descent, for instance, needs you to take sequential steps across the gradient of one element, and the problem becomes that in which order should I select these items. I could select them randomly, or I could pick a particular order. The best ideal scenario would be to pick gradients so that the empirical loss is always reduced at each time. So that preferred order is typically unknown, and that's why SGD picks these items completely at random. So the idea is to randomly reshuffle the data after a complete pass. So let me explain it through an example. This concept of distributed random reshuffling, which people use quite a lot when they implement gradient descent or stochastic gradient descent in distributed scenarios. So imagine that you have, let's say, a data set consisting of 4 points. Okay, so x1, x2, x3, x4 denote 4 points, and I assign 2 points to worker 1 and 2 data points 3 and 4 to worker number 2. And worker number 1 computes some gradients of points 1 and 2. Worker 2 computes gradients of points 3 and 4. Okay, so I'm still doing batch gradient descent. I'm not necessarily doing SGD at this point. Okay, so now worker 1 sends back the gradients to the master. Worker 2 sends back the sum of the gradients 3 and 4 to the master, and then master sums it up, makes an update, and then workers could potentially keep on updating the gradients. But if we keep the assignments of the points 1 and 2, 3 and 4 as static assignments to workers 1 and 2, we will run into a little bit of an issue. The issue is that worker 1 will always keep on computing gradients of 1, 2, and worker 2 will only compute gradients of 3 and 4. Particularly, this problem becomes even more challenging if we are doing stochastic gradient descent in a distributed manner like this. So what people do is that they sort of give fresh assignments to the workers after a few iterations or after a few epochs. So what they do is that they shuffle the data points. So for instance, 1, 2, 3, 4, we shuffle them to 2, 4, 3, 1. Just think of this as a permutation from pi at time 1 to pi to time 2. So we assign new points to these workers. So
Right,
worker,
I have a question.
Yeah.
So why do we need to do the shuffling? You said, meaning, what is the problem with the workers always doing the same gradient on the same points?
So imagine, let's say we have the same assignments. So workers 1 and 2 will keep on calculating gradients and make local updates only on those limited set of points, 1 and 2.
Would that slow convergence or?
Yes, so that might slow up the convergence, and that might not necessarily. So you might never see the combination of 2 and 4 together.
But, I mean, does it still converge but slower, or there's no guarantee for convergence?
So as far as convergence guarantees are concerned, convergence guarantees we have not yet looked at. In fact, proving the convergence or how this random reshuffling improves the convergence, that is something which is a very hard problem as far as I understand. We tried to search quite a lot of papers which tried to see whether this random reshuffling, what are the provable theoretical benefits as far as improving the convergence rate. There are only 1 or 2 papers and which show that this random reshuffling improves the convergence rate.
But the way it's done is more like empirical, like that's what it was.
Yes. So what the majority of the things that we have seen, essentially people use this random reshuffling as sort of an ad hoc step. And they almost always observe that this random reshuffling sort of provides fresh batches of data points to these distributed workers. Okay. So each worker is sort of not looking at a static batch of points and just working on that static batch, but each worker sort of gets fresh assignments. So that's my understanding, Salim. I mean, I think one problem that we are actually interested in is to understand, what would be the sort of interplay between the convergence rate and the communication overhead. And I'll maybe touch upon that later towards the end of my talk when I talk about open problems. So there's a very interesting sort of interplay between communication overhead and accuracy. It turns out that communication overhead is really bad for such shuffles which seemingly don't lead to too much improvement in accuracy. So it might be very interesting to characterize those shuffles which provide the maximum benefit in convergence, but perhaps those shuffles might actually be good in terms of not having so much communication overhead. Okay, so maybe that will become clear later when I talk about the scheme and the converse and all that.
Okay.
Okay. Yeah. So now, if you look at time t is equal to 1 and time t is equal to 2, what we need to do, what the master needs to do is ship new data points to worker 1. So worker 1 has x2 from the previous assignment, so it needs x4, and worker 2 has x3 from the previous assignment, and it needs x1. So of course, we can send uncoded transmission x4 and x1, but this is of course requiring 2 points to be sent. Instead, we can do uncoded. Instead of doing uncoded, we can do coded and send x1 plus x4. So we can observe that worker 1 already had x1 before, so it can remove it to get x4, and worker 2 had x4 and can remove it to get x1. Okay, so basically, this is the idea of coding. The question is, what is the trade-off between communication overhead and the amount of storage per worker? So this is what we call as pairwise coding, a very simple example. Of course, you can even have workers store the entire data set if that is feasible at all. Again, this is a toy example. So imagine now workers 1 and 2 had the capability to store all the 4 data points. So then we won't really need to send anything. So the communication overhead would be 0. And that's the problem that we want to understand, that what is the trade-off between communication overhead and storage at each worker for this random reshuffling problem. Okay. So there's a trade-off between storage and communication. So hopefully this motivation is clear. So I want to tell you a little bit about the information theoretic formulation of the problem and then tell you some insights about the results that we have for this problem. So as I said, we have this training data set of n points, d dimensions each. So we assume the points are IID and the entropy of the data set is n times d. N data points, each of dimension d. And they are connected through a shared link to k workers. Each worker has some storage. And the interesting part is that the storage of each worker is a time varying quantity. Okay, so we denote zkt as the storage of worker k at time t. And let's say at time t, the points that are assigned to worker k, we denote it by AKT. So AKT is the batch of points that are assigned to the kth worker for processing at time t. And of course, we have constraint on the amount of storage at each worker. So entropy of ZKT is S times T. So S is the storage parameter. Okay. On top of that, we also have potentially some excess storage at each worker. So before I proceed to excess storage, so entropy of AKT is N by K times T. So let me explain what this means. AKT is the batch of points that are sent to the kth worker at time t. Since there are k workers, and I'm assuming that every worker processes equal number of points, so every worker processes n by k points. So that's why the entropy of AKT is n by kT. So this is a fixed quantity. And the remaining part of the storage, each worker can store some functions of the other points that it is not assigned to process. Okay. So for the scope of this work, we focused on uncoded storage. So by uncoded storage, I mean the following. So if I look at worker number 1, its storage has two parts. The first horizontal line is A1T, the points it is processing. And then below that, you have K-1 partitions. So A21T is the points that the first worker stores about the points being processed by the second worker at time t. Similarly, A31 is the excess storage of worker 1, which is using to store points being processed by the third worker at time t, and so on and so forth. Okay. And similarly, we have the excess storage for the second worker and all the way up till the kth worker. Okay. So let's see. So let's say iteration at time t, the workers are assigned some batches, which we are calling through a permutation pi t. And at time t+1, we do a random permutation or random reshuffling. And so the workers are assigned new points, which are indexed by A1t+1, A2t+1, and so on and so forth. So the master node needs to send a communication, which we denote by a random variable x, which is, of course, a function of pi t and pi t+1. And we denote the entropy of the communication as RD. So R essentially denotes the normalized communication overhead of a particular scheme, which uses a communication X. Okay. And of course, entropy of X given A is 0. The reason why this is true, because A is the whole data set, and what the master node sends is only a function of the whole data set. So this is a simple constraint. So what we need as far as decodability, if I may use that word here, at worker K, what we want is that the new points for processing at time t+1 must be obtainable or must be decoded as a function of the transmitted information X and the local storage that it had in the previous time. Or in other words, in terms of entropy, we have entropy of the points at worker K time t+1 given X and the local storage at worker K at time t. This entropy must be 0. Yeah, go ahead.
For the, if I understand correctly, the new permutation, which is pi at time t+1, is it or you're happy if you have any permutation at the end? I don't know.
No, I mean, for any arbitrary permutation. So, think of pi t as some permutation of n points, and pi t+1 as another permutation.
But you decide that at the beginning, before transmitting, that I want to go from this permutation to this new one?
Exactly.
Or all you do is just
no. Yes, I fix the permutation.
Oh, okay.
I fix the permutation.
Would it make sense also to ask the problem where all I need is just the new data to be a new permutation?
Sure. Yeah. So that might be a slightly different version of the problem, where you don't care which points you get.
But maybe
again,
in that way, the distance between the two permutations is too small, and then this, you may just swap two things, and that's a new permutation, but maybe it won't affect it.
Yeah. But again, if you just swap two things, then that's not a good permutation as far as providing you a fresh batch of points at each worker.
Yeah. Okay.
So that's, so you also have to introduce some randomness in the permutation.
Okay.
If you want to really get any statistical benefit of doing this random reshuffling. So,
okay.
Yeah. Okay. So at this point, I mean, I'm not choosing what pi t is. I'm not choosing what pi t+1 is. These pi t and pi t+1 could be arbitrary permutations. Okay. And of course, the excess storage Also, each worker can also update the cache or update the local storage as a function of what it receives and what it has previously. So entropy of the excess storage given the transmitted information and local storage is also 0. Okay. So under all this, now what is our goal? Our goal is to find the minimum communication overhead. Okay. So that's the first goal. So, and I'll state two goals at this point, and then I'll explain which goal we are going to study. So the first goal is to understand if you give me any shuffle, any two consecutive shuffles, pi t and pi t plus 1, the goal is to find the minimum communication overhead R across all possible schemes. And when I say all schemes that satisfy the constraints of the problem, namely decodability, storage, delivery, and all those constraints that I just mentioned. So the first function R star pi t plus 1, you can view this as the optimal minimum overhead for any arbitrary pair of shuffles as a function of storage, number of workers, number of data points. And it turns out that finding this optimal rate as a function of arbitrary shuffles pi t plus 1 is a hard problem. We have some results on that, but I will not touch on those at this point. We can also then look at further variation of this R star pi t plus 1, which we call as the worst case rate. So worst case rate is the maximum communication overhead across all possible shuffles. So so you think of this as the following, that if I pick a pair of shuffles and I design the best scheme for a particular shuffle, and then an adversary comes and then the adversary picks among all possible shuffles the worst shuffle, which has the maximum overhead. Okay, so that's what we call as the worst case communication overhead across all possible shuffles. Okay, so our goal is to understand the worst case overhead or worst case communication overhead as a function of storage, number of workers, and the number of data points. Okay. So my goal will be to give you some results on this particular object, this R star worst case. Okay. So let's see, what do we expect as far as the behavior of worst case communication overhead as a function of storage. So first point to note is that storage cannot be smaller than a certain number. So this is storage per worker. So storage per worker cannot be smaller than n by k. The reason is this: I have n points, k workers. So every worker has to process n by k points. So storage cannot be smaller than n by k. And for people who have worked in distributed storage, so think of this as the MSR point, okay, minimum storage point. And it turns out that for this point, we have the answer to this question, which is, it turns out that the worst case communication overhead is n by k minus 1. And you can't go below this. So we have a converse and all that for this particular point. The other extreme is when every worker can store all the data points. So this is the MBR point. So think of, I'm just making a sort of not an exact analogy, but roughly speaking, this is the maximum storage point when every worker can store everything. So communication overhead is 0. And of course, we can join these 2 points, and by a simple memory sharing, or which is analogous to a time sharing argument, we can achieve all the points joining these 2 particular points. So intermediate values of storage, we can achieve any point on the line joining these 2 extreme points. So the question is this line optimal? It turns out that no, we can actually do much better than this line, and we can go significantly below this line. So we want to push this trade-off as close to as below as possible. That's the goal. Okay. So what I'm going to show you is some results for this particular trade-off, worst case communication versus storage, for this data shuffling problem. So I want to explain the idea through an example of 4 workers. Okay. So basically, we in our recent work, we came up with 2 schemes, 2 achievable schemes, and a lower bound for this trade-off. The first scheme is based on Mada Ali and Neeson's results on coded caching and how those ideas can be applied for this data shuffling problem. I'll first give you that scheme, and then I'll show you how to obtain lower bounds for this trade-off. And then I'll show you how Mada Ali and Neeson's scheme is actually not sufficient to solve this problem, and we need new ingredients to solve this problem. So let me very quickly go over this example of 4 workers. So for this 4-worker case, the range of storage is n by 4 to n. When storage is the smallest, n by 4, then essentially the optimal rate is 3n by 4, which was n times k minus 1 by k, which is 3 by 4n. And the communication is, the optimal strategy is to send A1 plus A2, A2 plus A3, and A3 plus A4. And you can readily check that no matter what the shuffle is, every worker will be able to essentially get all the data points that it needs, no matter what the random assignment, that is pi t and pi t plus 1. Okay. And we have a lower bound on the trade-off between rate and storage, which is given by these points. And what I'll show you next is an achievable scheme, which is sort of inspired by Madali and Neeson's result on coded caching, which achieves this red curve. So this red curve and the black curve, which is the lower bound, there is a gap between these two. Okay, so before I talk about the gap and all that, let me give you the basic idea of the scheme for one particular point. So I'll focus on this curve, this 7n by 16 and 3n by 8. So the first red point from the left. Okay. So let me explain the achievability for this 4-worker case. So let's say we have 4 data points. So let's say we denote the points as x1, x2, x3, x4, and each point is of dimension d. So what we do is that we break each point into 4 parts. So we assume that the dimensionality d is large enough, or if I do a bitwise representation, then we break the point into sub points or sub messages, if you may want to call that, as follows. So we break each point into 4 parts and label it by x11, x12, x13, and x14. Okay. And let's see what happens as far as the storage strategy of the workers. So worker 1 will, of course, store x1 completely. Worker 2 will store x2 completely. Worker 3 stores x3, and worker 4 stores x4 completely. Of course, they have to store these because these workers are processing these 4 points individually. But since they have excess storage, so how much excess storage they have? The storage is 7 by 4. So I put n is equal to 4, and I get s is equal to 7 by 4. So each worker can store 3/4 of a point in total. So each worker stores the following. So worker 1 stores those additional chunks in which it has its own index. So worker 1 stores x21, x31, and x41. And similarly, the other workers store correspondingly those subpoints in which they find their own index. So now, if there are no questions about the storage strategy, let's see what happens next. So let's say a new shuffle comes. So at the next time, let's say the data points are shuffled. So that worker 1 is assigned to process 2, worker 2 is assigned to process 3, 3 is processing 4, 4 is processing 1. So now worker 1, let's see what does worker 1 need. Worker 1 already has x21 in its excess storage. So it needs x22, which is available at worker 2. And we can see that worker 2 is now processing the point x3, and it already has x32. So it needs 2 other chunks, x31 and x3, 3 and x34. So what we can see is that this x22 and x31 are sort of mutually available at workers 1 and 2, and they are needed at each other. So we can sort of take a coded combination of these 2 items and send it so that it's useful for both workers 1 and 2. So this is pretty much the basic idea behind the coded caching scheme of Madali and Neeson, which is sort of carefully adapted to this particular problem of coded data shuffling. And we can similarly create, these pairwise symbols, which are useful for 2 workers at a time. Okay, and let's see the amount of communication overhead for this scheme. Note that each point was broken into 4 chunks. So each sub chunk is of size 1/4. Okay, and we are sending a total of 6 chunks, 6 coded chunks. So the total rate is 6 times 1/4, which gives us 3/2. Okay, so this is the basic idea of the adaptation of Madali and Neeson scheme for this particular problem. Of course, we need to do one more thing. Once these data points are transmitted, when these coded chunks are transmitted, workers need to update their storage. So this is how they update their storage. So worker 1 now is storing x2 completely at time t plus 1. It is storing x31, so it only stores those chunks of the 3 remaining points which have index 1 in it. So it throws away some points. So it throws away some chunks because it only has storage of 7 by 4. So worker 1 stores x31, x41, and x11, and so on and so forth. So this step is a new step which is not present in the classical coded caching literature. In particular, each worker should also try to update the storage, excess storage in a particular way so that it sort of maintains the structure. By maintaining the structure, the idea is that, if at the next time epoch, a new shuffle comes, the structure of the excess storage remains the same. So the same coding strategy can be used over and over again. So that's sort of a new element which is involved in this problem, which is not present in the classical coded caching literature. Okay.
And Ravi, I have a question about the previous slide.
Yeah, go ahead.
So here you presented this scheme for going from certain permutation at time t, which is 1, 2, 3, 4, to another permutation at time t plus 1.
Yes.
2, 3, 4, 1. But this
Yes.
would also, this kind of thinking would also work to any permutation.
Exactly. Yes. So I'll tell you the general scheme. The general scheme is exactly like Nadali-Nielsen. So this scheme works. I mean, so I gave you an example just to illustrate the ideas. But of course, the scheme that we must develop or we have works for any permutation pi t and pi t plus 1, no matter how the permutation is selected. Yeah. Okay. So before I tell you the general scheme, I want to talk about lower bounds as well. So these are the lower bounds that we have on the communication versus storage trade-off, or rate versus storage trade-off. So everybody will agree with me that the first bound, S is greater than n by 4, this is a trivial bound, because every worker should store at least 1/4 of the total amount of data if there are 4 workers in the system. The question is, how do we obtain these other 3 bounds, 5n by 4 minus 2s, and so on and so forth. So I'll try to go over the basic idea of the converse proof. So let's assume we have a general uncoded placement strategy. And let's look at any data batch, sub-batch, ATI. So ATI is the batch being processed by the ith worker at time t. Since we are only focusing on uncoded storage, and we allow arbitrary division of each data point in any batch, we can potentially partition them into 2 raised to power k minus 1 partitions, corresponding to the other k minus 1 workers. Okay. So each worker k stores AT subscript WI in its access storage if the worker k belongs to the set W. Okay. So for instance, AT1, so think of this as batch being processed by worker 1 at time t. We can break it into those parts that are stored nowhere, those parts that are stored at worker 2, at worker 3, at worker 4, parts that are stored jointly at 2, 3, jointly at 2, 4, jointly at 3, 4, and 2, 3, 4. There's a typo here. Okay. So from these, we first have the data size constraints. That entropy of all the 4 batches should be ND. And then we can write this constraint in terms of these newly defined partition variables, ATWI. And what we call this entire summation as XTD. So what is this XTD? XT, essentially, you can think of this as a variable. X0, for instance, is some of those items which are stored nowhere in excess storage. X1 is those items, is some of the entropies of those items which are stored uniquely at 1 worker. X2 is sum of entropy of those items which are stored uniquely at 2 workers, and so on and so forth. So X0 plus X1 plus X2 plus X3 must add up to 1. So that's the first constraint that we get. Okay. And of course, then we also have excess storage constraint, that each worker has certain amount of excess storage, so it cannot exceed that. So we get this entropy of these variables is less than or equal to this excess storage. And when we translate these constraints in terms of these newly defined variables, X1, X2, X3, this is the constraint that we get. Okay, so these are 2 basic constraints. And now, in order to obtain a lower bound on the rate, what we do the following. So we follow a certain trick. So the first trick is that we pick a certain shuffle. So you pick any shuffle, and you try to get a lower bound on the rate for this shuffle. Now, naturally, this should also be a valid lower bound for the worst case rate, because the worst case rate cannot be smaller than the rate of any arbitrary shuffle. Okay. So what we do, we pick a certain shuffle, which we call as the cyclic shuffle. So what does the cyclic shuffle look like? So let's say the 4 workers are assigned the following batches, A1, A2, A3, A4 at time t. And just think of a cyclic shift of these 4 by 1 unit. So now I shift all these to the right by 1. So worker 1 is assigned 4, 2 is assigned 1, 3 is assigned 2, and 4 is assigned 3 at time t plus 1. So the logic behind the lower bound is the following. So if we observe that from Z2, Z3, Z4, so Z2, Z3, Z4 are the contents at the workers 2, 3, and 4. So they must, of course, be storing A2, A3, A4 at time t. And once these new shuffles are assigned, then a communication X occurs. So from the communication X and Z2, worker 2 should be able to decode A1. Why should that be true? This should be true because of the decodability constraint. So if the scheme is reliable, or if it satisfies decodability constraint, then worker 2 should be able to decode A1 by using its local cache Z2 and the communication X. So if I look at all these 4 variables, that is, if I look at Z2, Z3, Z4, and X, I should be able to decode the entire data set. Okay, so it's a very simple logic. Or in other words, the entropy of the data set given Z2, Z3, Z4, and X should be going to 0, or should be exactly 0. So that's the first step. We start with that basic inequality, that entropy of A is n times D. which is n data points, each of size d dimensions, which should be equal to z2, z3, z4, and x. Then we apply chain rule. So we essentially get these three terms. And then we bound them as entropy of x is less than or equal to the rate, plus entropy of z4, plus 3 given x, z4, a3, and a4. And these terms are added again due to the fact that worker 3 should be able to get a2 and a3 once it gets the communication x. And for this part, I'm invoking the fact that we're looking at a cyclic shuffle. So once we put all these things together, it's a matter of basically going back and looking at how these variables x's were defined. And then, Salim, due to interest of time, I'm not going into too much details of this part. So,
Yeah,
but
I think maybe we have around 5 more minutes.
5 more minutes, right? Okay. So essentially, it's a matter of carefully playing with these entropy terms using the definitions of the data partitions, and what we end up with is the following. What we end up with is a lower bound on the rate. So r pi t plus 1 is greater than or equal to these functions of x0, x1, x3, x4. So remember, what was these x0, x1, x2, x3, x4? These were the essentially functions of the entropy of the data partitions, which were indexed by how many workers are storing a particular data point in their access storage. Okay. So now, if you remember, these variables x0 till x3 were also satisfying a certain set of other constraints, which was the data size constraint and the access storage constraint. So to get the best lower bound, we need to solve a LP. So the worst case rate is, of course, greater than or equal to the minimum of this expression, subject to the three constraints. So the three constraints are the data size constraint, the access storage constraint, and the fact that these variables are sum of entropies, which should be non-negative, or the sum of the entropies is greater than or equal to 0. And then it all boils down to solving this LP. So for instance, I'll give you an example. So we eliminate x0 from the objective function to get this. And then we eliminate x1 from the objective function to get this. So we get a bound on worst case as 5n by 4 minus 2s plus x2 by 3 plus 3x4 by 3x3 by 4. And then we throw these last two terms away. And that gives us a first bound on worst case as 5n by 4 minus 2s. Okay, so we get this first bound by eliminating x0 and x1 in the LP. Similarly, we next eliminate x1 and x2 in the LP to get the second bound. And then we eliminate x2 and x3 in the LP to get the fourth bound. So it turns out that these bounds are all actually solutions of the LP depending on which variables you eliminate. And this elimination of variables actually also sort of makes quite a lot of intuitive sense. So x0 and x1 being eliminated means that, and leading to the first bound essentially corresponds to the first line or the first hyperplane corresponding to the storage, the smallest set of storage values between n by 4 and 2n by 4. And it turns out that for this particular example, x2 and x3 variables are actually 0 in the optimal solution. So they don't really have any role to play in the lower bound as well. And so on and so forth in the other three bounds. Okay. So the general achievability, so now let me just go back and tell you the general achievable scheme. We consider a set of storage values as follows. And we follow basically the main idea behind Madali and Neeson's scheme, which is to divide each data point into k choose I subpoints and label each subpoint by a set of size I. And then each worker stores the assigned data points as well as those subpoints where it falls in this particular set W. So each worker k stores at least k minus 1 choose I minus I subpoints, and needs at most k minus 1 choose I subpoints. And in the delivery phase, then we combine these I plus 1 coded symbols. So if you remember, for the 4 worker example, we saw that 2 points were combined. So essentially these were order 2 symbols. So more generally, depending on the storage values being considered, we can combine I plus 1 symbols and send a XOR or a coded version of these I plus 1 symbols, which will be simultaneously useful for I plus 1 workers at the same time. Okay, so the worst case rate by using this Madali-Neeson's strategy essentially is 1 over I plus 1. 1 over I plus 1 comes because I am combining I plus 1 symbols. Then the second term is n by k times k minus 1 choose I, which is the number of subpoints needed by a worker in the worst case scenario. K is the number of workers, and 1 over 1 by k choose I is the size of a subpoint. Okay, so once you simplify all these things, what we get is a simple expression. The worst case rate achievable is n by k times k minus I divided by I plus 1. So it looks remarkably similar to what was achieved for coded caching. Essentially, we have a local gain. So this k minus I corresponds to the local gain, like how much points each worker can store in its excess storage. On top of that, by doing this coded transmission, we get a global gain, which is 1 over I plus 1. Okay. So to summarize, we have this, the first scheme, the Mudali-Neeson adapted scheme, gives us the lower convex envelope of this falling storage versus rate pairs. And on the other hand, we have a lower bound, which is obtained by solving this LP, and which gives us a lower convex envelope of the falling storage communication rate pairs. It turns out that these bounds don't match. Okay, so which is the interesting and surprising part, that Mudali-Neeson scheme was in fact optimal for the coded caching problem under uncoded storage. However, it turns out that that scheme is not optimal for this particular problem. And there is a gap between the lower bound and the achievable scheme, and the gap is at most k by k minus 1, which is less than or equal to 2. Okay. So next, so essentially this figure shows the gap between the bounds when we have 1,000 data points and 10 workers. And gap exists at certain values of storage. So let me now talk a little bit about closing the gap, which I think is one of the interesting parts of this work. And that how do we close the gap? Which one is loose? Is the lower bound loose or is the upper bound loose? So it turns out that the lower bound is not loose, and we can improve upon the Mudali-Neeson type of coded shuffling scheme. And I'll focus on one particular point and try to illustrate the key idea behind this scheme through this example. So let's focus on this particular point when storage is 2n by 4 and rate is n by 4. Okay. So this scheme requires two ingredients, it turns out. It requires the idea of interference alignment, and it requires the idea of coded shuffling. So it sort of takes two things together and put them together in an interesting way. So let me explain the scheme through this example. Suppose we have, again, 4 workers, 4 data points. So first thing we do, we break the point into 3 parts as opposed to 4 parts. So we break point x1 into 3 parts, x12, x13, x14. And similarly, x2 is broken into 3 parts, x21, x23, x24, and so on. And the excess storage, worker 1 stores those parts of points 2, 3, 4 in which it is the index. So note that it is a little bit different the way we break the data points. We are doing it explicitly to fill up the excess storage, whereas in the original Mudali-Neeson scheme, it was sort of broken to fill up the whole storage. So that's the main first difference. And now let's say we have a shuffle. At time t plus 1, we get assigned these same points, 2, 3, 4, and 1. Now, our goal is to show that we can achieve a rate of 1. R is n by 4. If I put n is equal to 4, we get R is equal to 1. So let's see the idea behind the scheme. So let's look at worker number 2. Worker number 2 wants point x3 at time t plus 1. So if we look at x34 is a chunk which is available at worker 3, available at worker 4, and it is needed by worker 2. However, if x34 is sent in any way, it will cause interference at worker 1. Okay, so this x34 is an interference unwanted item for worker number 1. Okay. Similarly, let's look at this chunk x42. So x42 is available at worker 4. It's available at worker 2, and it is needed by worker 3. However, x42 is also interference at worker 1. So if this x42 and x34 are sent separately, then these two guys will be sort of completely useless for worker 1, and they will be sort of interference for this worker. So the idea is that, how about we combine these two things together? That is, we want to align the interference elements at any particular worker as much as possible, and make the space spanned by interference at these workers to be spanning as little total space as possible. Okay. So instead of sending them separately, what we can do, we can combine these two items together, and then let's see what does the whole scenario look like. We can see that this coded chunk is available at worker 4. It is needed by worker 3, and it is needed by worker 2. So it is simultaneously useful for workers 2 and 3. And interestingly, we have reduced the interference from 2 items to a 1 coded item. Okay. So that's the basic idea behind this aligned coded data shuffling scheme, that while creating these coded chunks, we have to be careful in trying to see how much interference is being caused at each worker, And at the same time, are there opportunities to combine these coded chunks to reduce the interference impact at each worker? So for this example, when you work out the example, you will see that there are 4 coded chunks. Each coded chunk essentially is, you can view this as an aligned chunk, which only causes interference at a single worker. So there are 4 such chunks. And it turns out that the second chunk, x41 plus x13, is actually available at worker 1. So worker 1 needs 2 items. It needs the third and fourth chunk. The first one is interference for it. The second one is available at it. And it's the same scenario for all the 4 workers. So we can actually send 3 linearly independent combinations of these 4 items. And that will be useful to help allow successful decoding of all the 4 workers simultaneously. So the rate is actually 3 times 1/3, because each chunk is of size 1/3, and that gives the rate as well. And this is the optimal scheme. So the aligned coded data shuffling scheme is actually the scheme that achieves the information theoretic lower bound for this problem. Okay. And then there is a storage update strategy and relabeling, which I will skip for now. But I'll be happy to take questions later on if there are any on this. So it turns out that, at least for this example, the upper and lower bounds matched. So the upper bound is now the one that's coming from the aligned coded data shuffling scheme and not the original shuffling scheme. More generally, we also have a general result which shows that for certain storage values, this aligned coded data shuffling scheme exactly matches the information theoretic lower bound. Even though we don't have a full result for all storage values, but at least for certain storage values, this aligned coded data shuffling is exactly optimal. Okay. So it further reduces the gap, as you can see, for the same set of parameters, n is 10,000 and k is equal to 10. And gap exists only at these integral values. And it turns out that the maximum gap for the aligned coded data shuffling scheme reduces from 2 to 7/6. 7/6 is the gap result that we have using this new scheme. Okay. So let me conclude here by saying that we looked at information theoretic trade-offs in data shuffling. The main idea here, the main message, is to exploit coding and excess storage in a clever way to reduce the overall communication overhead of this data shuffling problem. The first scheme that we proposed was inspired by Madali and Neeson's work on coded caching. We also came up with novel lower bounds or converse results for the data shuffling problem. And the first scheme number 1 is shown to be within a multiplicative gap of 2 of the lower bound. However, interestingly, this bound is not optimal, and we need new ingredients to settle this trade-off, at least partially as of now. So we combined the ideas of alignment and coded shuffling. And what we have is so far is the scheme is optimal for certain storage values, and it improves the multiplicative gap to 7/6. There are several open problems. Clearly, the first open problem is closing the gap for all storage values. Our conjecture is that this lower bound that we have, which we obtained through this LP-based approach, is in fact optimal. The second problem, I think it is interesting, and it is sort of related to the sub-packetization issue in coded caching. We are sub-packetizing or dividing the data into a certain number of chunks. What if we have constraints, or the D itself may not be too large? Then what are the trade-off between communication and storage as a function of the data divisibility constraints? And then the third problem is from the worst case rate to rates for arbitrary shuffles. So that is another interesting problem. So let me stop here and take any questions if you may have.
Yeah, thanks a lot, Ravi. So I don't know if anyone has questions, maybe they can ask right now. Yeah, I don't know if there are no questions, then I think we can conclude here. And thank you again a lot, Ravi. And then so this talk will be posted on YouTube, and then people can also interact on YouTube in the comment section.
Okay, sounds good. Okay, thank you. Thanks a lot.